Okay, so we left off where we had this here as my gain, my differential gain, but remember this is for small signal now. That's my small signal gain, which was the same as what we had for DC. Now we need to look at the common mode gain. The common mode gain, now for DC, the common mode gain was just simply 0. So let's look at what it is for small signal. Well, remember for common mode, what we had here is that the common mode we had that VB1 is equal to VB2. That's the whole point for common mode, is that the voltages are the same. But remember, back at the beginning of our discussion of the operational amplifier, we had two equations here, where the differential voltage was V1 minus V2. So we're not talking about VB1 or VB2, we're talking about V1 minus V2. And that the common mode voltage was V1 plus V2 over 2. So now I'm not going to do this, it's very easy, but solve equations for V1 and V2. If you solve those equations for V1 and V2, you get V1, which is going to be my VB1, is equal to my common mode voltage plus my differential voltage divided by 2. And then that V2 is going to be VB2, which is my common mode voltage minus VD over 2. So what we get here, what we're going to look at here is we have, remember, my equation for V out is equal to, this equation doesn't change, minus beta. So this is just rewriting the equation we had in a previous video. VB2 minus VB1 over 2R pi plus RB. And so what we're going to do here is we're going to substitute these in here. Into the equation. I'm sorry, I'm substituting them into the wrong equation here. We're going to substitute because we're wanting to keep track of the early voltage stuff. So we're going to not do this equation. We're going to do the ugly equation up here. I scrolled over it somewhere. There we go. We're going to substitute it into this mess here. So we're going to substitute this VB1. This VB1 is going to get substituted into here, and this VB2 is going to get substituted into here. Okay, so basically more algebra. That I will skip. I don't think the algebra provides any insight. What provides insight is exactly what we're going to do here. And the reason we're going all the way back to here is we're trying to determine exactly what kind of the thing happens with the common mode voltage here. The differential voltage, we just ignored the effect of RO because, well, we're saying it's always going to be big here. But we don't want to ignore it here because we're trying to see what happens with the common mode voltage. Okay, so then what we get here when we do that is we get V out is equal to beta RC over 2R pi plus RB times my differential voltage minus, and then what we're going to have here is GM RC over 1 plus 2, 1 plus beta RO over R pi plus RB VCM. This here we're going to call the common mode voltage gain. Now, if RO equals infinity, ACM is just equal to 0. So if we have an ideal current source, the common mode gain is just simply 0 because we get an infinity in the denominator, and so we're just going to get 0. That's why we had to go back to the original equation. We're not necessarily assuming RO is infinity at this point because we're really wanting to make sure we see the effect here. And so what we end up getting here is we can write V out. This is simply just, and I know I have to make a small correction here previously, you probably already caught it, AD VD plus ACM VCM. So this is an important equation right here. And now you might say here, wait a minute, where's your negative? Because you had a negative back here. The negative really shouldn't be there, because let's go back and see why the negative shouldn't be there. This is VB2 minus VB1. VD is VB1 minus VB2. So I would need to actually put a negative here because it would be negative VD, because I got to switch the order of that, which then makes this positive, or I'll just erase it, and that's positive. So those are positives. Obviously sine errors are critical, and I made some in the previous lessons. Hopefully you had already caught them. So let's summarize here at this end of our video here to make sure we have all the equations correctly here. Well, it's not the end, but before we talk about common mode rejection ratio, let's summarize here. So differential voltage gain, DC, AD is GM, GM over GM RC over 2. AC, or what I should say, instead of AC, we'll say small signal. It is AC, but we got to be careful because it has to be a small signal. We get that AD is beta RC over 2 R pi plus RB. And then of course if RB is 0, that reduces to the same equation for DC. Alright, then we have common mode. So for DC, AD is simply 0. So that's easy. And then for small signal, and it's not AD, CM. Small signal, we have Cm is equal to minus Gm Rc over 1 plus 2 times 1 plus beta Ro over R pi plus Rb. Okay, now the last thing we're going to talk about in this lesson, and then the next lesson we'll go through an example, is what we're going to talk about here is we're going to talk about the common mode rejection ratio. Not ration, ratio. So for an ideal op amp, we have Ro being infinity, this little Ro here, is infinity, and since it's infinity, the common mode voltage gain is 0, which is what we would want. It's 0 in both cases. So in essence, what we're saying is if we put the same voltage on either terminal, we're getting nothing out. And again, that's what we'd want because this is a differential amplifier. If we have the same voltages on the same terminals, we don't want to get anything on the output. DC, no problem. Small signal is where we have the issue. And so in data sheets, if you've looked through any kind of data sheets, you might see the common mode rejection ratio. And this is a very important parameter here because you want it to, quote, be large, because that means that if the voltages on the inputs were the same, you're getting very little output on the op amp. So basically, if you have the same voltages, same small signal on the inputs, you're not going to get any kind of output from that. And so the definition here for the common mode rejection ratio, it's CMRR, is simply the magnitude of AD over ACM. And then this is often reported in decibels. And so I'll just put it here, not 10 dB. And this, because I've been dealing with voltages, would be a 20 log of AD over ACM. And if we just look at this here and do some of the division here, and so basically what we're going to do here, and I'm not going to show you the work, we would be looking at this here and this one here. Now we're looking at the magnitude, so the negative's going to go away, and you're going to have to look at some things, you know, canceling out and everything else. But using those equations, you can get here that the common mode rejection ratio, now this is not in dB, this is just a number at this point, is 1/2 times 1 plus beta plus 1 IQ RO over VT beta. And we could write this slightly different. Using some GMs and stuff like that. I'm not sure why they write the equation this way, or why the resource I'm using writes the equation this way, because, you know, we do have that GM, for instance, is IQ over VT, and then, you know, you have beta is equal to GM R pi, So you could have GM over beta is equal to 1 over r pi. So we really could simplify this equation, and let's see here, make sure I'm not making any sort of stupid things here. I mean, this equation is correct, but you really could rewrite this equation here as the common mode rejection ratio is 1/2 times 1 beta plus 1 over beta times RO over r pi. So let's just double check that. In some ways I think this equation looks a lot simpler, but let's just double check that here. So IQ over VT, we agreed that's GM. So if we did that here, I'm going to erase this here. That would be GM. GM over beta is 1 over r pi. Yeah. So we could easily get this equation here. So you can use either equation. You obviously would get the same answer, but then of course in any kind of problem or homework or anything like that, you have to make sure to know what to report your answer in. And it's often reported in decibels just because these tend to be pretty big numbers, because RO tends to be pretty big. So that's why we tend to write them in decibels, and in data sheets, as we see, it's in decibels as well. And so typically the general rule of thumb is the higher the common mode rejection ratio is, the better. And so again, we're still not at an op-amp yet, but the reason I keep talking about that it isn't an op-amp is the first part of an op-amp that we've seen is a differential amplifier. So that's why, again, of course, we're studying these differential amplifiers, and so we can build an op-amp. And the first part of it is a differential amplifier. So we want to have high common mode rejection ratio. And again, what that means is that if we had the same, like for instance, let me just write it down. Let's just say we had V1 equals 1 cosine omega t millivolt, which is equal to V2. In theory, V out should be 0. But it won't be, because of ACM for small signal. It won't be 0 because of ACM for small signal. And so we want it to be 0. So the higher this common mode rejection ratio is, that means the closer this V out would be to 0, given that these V1 and V2 were the same.